This is part 3 of a series on KNN. In this video, we'll look at the curse of dimensionality and lazy learner. This video was produced in Korean and translated into English. The audio was generated by AI, text-to-speech. In the last video, we looked at the different types of distances and data normalization. We also looked at the optimal k-value and decision boundary. In this video, we'll first look at the curse of dimensionality problem, which can occur when the data is in a high-dimensional space. Next, we'll look at the lazy learner, also known as instance-based learning. Finally, let's implement a KNN classification model using scikit-learn's KNeighborsClassifier. Now let's look at high-dimensional data that has many features or attributes. The more features in a dataset, the higher the dimensionality of the feature space. For example, the iris dataset has 4 features. Each data point is mapped to a single point on a 4-dimensional feature space. This space is 4-dimensional, so it's difficult to draw. Since the target Y consists of 0, 1, and 2, the data points in this space can be distinguished by different colors like this. Similar data points are closer to each other and are grouped together, forming clusters in this space. We cannot imagine the shape of a data distribution in a 4-dimensional space. But we can mathematically compute the distance between 2 data points. Next, let's look at the MNIST dataset with higher dimensions. Each data point in the MNIST dataset is a 2-dimensional image of size 28 by 28. This image can be represented as a 784-dimensional vector, which is 28 times 28. Each vector can be represented as a single point in the 784-dimensional feature space, like this. That is, the image is represented as a single point in this space. Even higher dimensional image, such as full HD image, is represented as a single point in a higher dimensional feature space. In this space, similar images will also be grouped together. Even in high-dimensional spaces, we can mathematically compute the distance between 2 data points. And this distance can be used to measure the similarity between images. However, in high-dimensional spaces, it is difficult to measure the similarity between images due to a problem called the curse of dimensionality. The iris dataset cannot be said to be high-dimensional because it has only 4 features. But the MNIST dataset can be said to be high-dimensional because it has 784 features. Therefore, when classifying MNIST images or higher-dimensional images using KNN, the curse of dimensionality problem must be considered. This problem is important because most of the data used in real life is high-dimensional. Now let's take a closer look at the curse of dimensionality. Since KNN is an algorithm that uses the distance between data points in the feature space, its performance may deteriorate as the number of features increases. This phenomenon is called the curse of dimensionality. As the number of features in a dataset increases, the amount of data required to cover the feature space increases exponentially. Now let's look at why this phenomenon occurs in high-dimensional spaces. Let's say we have a dataset with 3 features, whose values range from 0 to 1. The data points will be distributed within a unit cube, like this one, where all sides are of length 1 unit. We want to find neighbors that lie within a cube, centered around the test data point that contains 10% of the training data points. That is, we want to set the k value so that the value of k over n is approximately 0.1. N is the total number of training data points. The length of one side of this small cube is s, and the volume of this cube is s to the 3rd power. This volume is k over n. So S can be written as follows, where P is 3-dimensional. Then, the length of one side of this cube is 0.464. If P is 10, i.e. a 10-dimensional feature space, S increases to 0.8. This is 80% of the length of one side of a full cube. This means that in high-dimensional space, the neighbors are far away from the test data point. As P increases, S also increases rapidly, so the size of the cube containing k neighbors also increases rapidly. Let's say we have a test data point and several training data points with different classes, arranged in a low-dimensional feature space like this. This test data point can be easily classified as class 0 because it is closer to the training data points, which are class 0. Measuring distances makes it easy to find the neighbors of the test data point. But in higher dimensional spaces, things are different. As you can see in the left figure, even the 10% neighbors are far from the test data point towards the corners of the cube. Therefore, the distance between this test data point and the closest training data point will be similar to the distance between this test data point and the farthest training data point. That is, as the dimension of the feature space increases, the ratio of the maximum distance to the minimum distance approaches 1. Since it is difficult to know which training data point is closer to this test data point, we cannot properly classify this test data point. These two data points are also not close to each other. If one is far behind the screen and the other is in front, these two data points can be very far apart. Therefore, in very high-dimensional spaces, the KNN algorithm that utilizes neighbors may not work well due to the curse of dimensionality. Next, let's see whether the ratio of maximum to minimum distances decreases as the dimensionality of the feature space increases. Load the MNIST dataset. Each image in the MNIST data has 784 dimensions, which is not very high-dimensional, but can be considered somewhat high-dimensional. We write a function that computes the distances between a single data point and all other data points in a given dataset. Randomly choose a single data point from the dataset. Remove the chosen data point from the dataset. Compute the distances between the chosen data point and all other data points. Return the minimum distance and maximum distance. Now let's measure the ratio of the maximum to minimum distances between one NIST image and all other images in the 784-dimensional feature space. We measured the ratio 10 times and averaged the results. The result was 4.78. Next, let's reduce the MNIST vectors to 5 dimensions using PCA. And then measure the ratio in the same way as above. The result was 36.23. We can see that in low-dimensional spaces, this ratio is much larger. Next, let's look at what the lazy learner is. KNN is often called a lazy learner. KNN does not build a model during training, but instead simply memorizes all the training data points. First, let's look at eager learning, as opposed to lazy learning. This is also called model-based learning. We first fit a model to the training data, and then we use the trained model to make predictions on test data or new data. Model-based learning takes time to train, but once trained, it can make predictions quickly. It is typically faster than instance-based learning. Model-based learning often has higher prediction accuracy than instance-based learning because the model is trained on a large dataset and can generalize to new data. Most machine learning models, such as decision trees, support vector machines, and artificial neural networks, work this way. Now, let's look at lazy learning or instance-based learning. In instance-based learning, no model is built first. It simply stores all the training data and uses the stored data to make predictions on test data or new data whenever needed. Instance-based learning is typically slower than model-based learning because it must compute something between the new data points and all training data points every time a prediction is made. KNN is a typical example of instance-based learning. It is called a lazy learner because the trained model is not created in advance. Finally, let's write some code to perform KNN classification using scikit-learn's KNeighborsClassifier. We will use the iris dataset. Load the iris dataset. X is the feature and Y is the target class. The number of features is 4, and the number of data samples is 150. The target class Y has 3 categories, classes 0, 1, and 2. Split the dataset into training, validation, and test data. 60% of the dataset is used as training data, 20% as validation data, and 20% as test data. The validation data is used to determine the optimal K value, and the test data is used to evaluate the final performance of the model. Normalize the data with z-score. Since the features have different sizes, data normalization is required. Compute the mean and standard deviation from the training data. We then normalize the training, validation, and test data by applying the mean and standard deviation of the training data. Set the value of k to the square root of n. N is the number of training data points. Build a KNN classification model. We used Euclidean distance. Fit this model to the training data. Since KNN is a lazy learner, no learning is performed at this step. It simply stores the training data points and the parameters. Predict the class of validation data. The actual learning takes place at this stage when test or validation data is provided. We measure the accuracy on the validation data. Next, let's determine the optimal value of k. While changing the k value from 2 to 20, we build each KNN classification model with that k value, fit each model to the training data, predict the class of the validation data, and then measure and save the accuracy on the validation data. Then we find the optimal k value that gives the highest accuracy. Since we started the for loop at 2 on the previous page, we add 2 here. And we observe how the accuracy changes as the value of k changes. Finally, we use the test data to measure the final performance of the model. Let's check the results. The value of k calculated as the square root of n is 9, and the accuracy on the validation data is 0.967. This figure shows how the accuracy changes as the value of k changes. The optimal value of k is 5. When k was 5, the final accuracy on the test data was 90%. The iris dataset is very small, so the results can vary greatly depending on where you choose the validation or test data. Let's run this code. This time, the results are as follows. So far, we have looked at the curse of dimensionality and lazy learner and implemented the KNN classification model using scikit-learn. In the next video, we will look at the weighted KNN.